There is a quiet crisis hiding inside every major airport on the planet, and most passengers walk right past it without a second thought. The gates are too small. Not metaphorically, not in terms of comfort or amenities, but literally, physically too small for the next generation of aircraft that airlines desperately want to fly. Boeing's 777X is one of the largest commercial aircraft ever built, stretching nearly 77 meters from wingtip to wingtip. That wingspan creates a fundamental problem the moment the aircraft tries to park at a standard gate. The solution Boeing engineered is one of the most quietly brilliant pieces of aviation design in recent memory. And it folds. Airports around the world use a classification system developed by the International Civil Aviation Organization to categorize aircraft by size and assign compatible infrastructure accordingly. Code E gates are designed to accommodate wingspans between 52 and 65 meters. The Airbus 380, one of the widest commercial aircraft ever operated, fits within this envelope at 60 meters across. The 777X in its fully extended configuration does not. At nearly 77 meters, it falls into Code F territory, a category that requires significantly wider taxiways, larger aprons, and gate spacing that most legacy airports simply cannot provide without billion-dollar reconstruction projects. Heathrow, one of the busiest and most slot-constrained airports on Earth, operates primarily with Code E infrastructure. Without a structural solution, the 777X would be locked out of the most valuable routes in global aviation. Boeing's answer was to make the last 3.5 meters of each wingtip articulate upward on the ground. When the aircraft lands and slows below a certain speed threshold, hydraulic actuators rotate the folding wingtip sections upward at roughly 90 degrees, reducing the total ground footprint to approximately 64.8 meters, comfortably within Code E limits. The mechanism is locked in the extended position during flight, where aerodynamic loads are enormous and any movement would be catastrophic. Sensors, redundant locking pins, and flight control logic all work in concert to ensure the tips are fully deployed and confirmed before takeoff clearance is ever requested. The system adds weight, complexity, and maintenance requirements, but Boeing calculated that the trade was worth it. Access to Code E gates at slot-constrained airports like Heathrow is not a convenience. It is a commercial lifeline. Heathrow operates at roughly 98% capacity on most days. Every slot is worth millions of dollars annually to the airlines that hold them. Airlines flying the 777X need to operate it on their highest demand, highest yield routes, and those routes almost always pass through airports like Heathrow, Frankfurt, and Singapore Changi. If the 777X could only access Code F gates, the number of compatible airports worldwide would shrink dramatically, and the economic case for buying the aircraft would collapse. The folding wingtip is not an aesthetic flourish or a novelty engineering exercise. It is the mechanism that makes the aircraft commercially viable on the routes that matter most. What the 777X folding wingtip reveals is something fundamental about how aviation engineering actually works in practice. The most elegant solutions are rarely born from pure technical ambition. They emerge from the collision between physical possibility and operational reality. Boeing did not design folding wingtips because the technology was available. They designed them because the alternative was an aircraft too large to land where passengers actually need to go. Every meter of that wingspan generates lift efficiency that reduces fuel burn across thousands of flight hours. But none of that efficiency matters if the aircraft cannot access the gates that connect it to the global network. The fold is not a compromise, it is the entire point.